Hi everyone! This is the second half of lesson 4.6 and today we'll be covering the second fundamental theorem of calculus. So if you think back to what we did yesterday, instead of having a numerical value b as the upper limit of integration, suppose we had a variable x as the upper limit. And you're going to notice as we work through these, we're going to switch then to using t as the variable of integration. So what the second fundamental theorem of calculus states is that if a function f is continuous on some interval I, open interval, and it contains a, so a is an x value, then for all x element of I, so remember what that cool math symbolism means, the upside down a is for all x, that's the Greek letter epsilon in there, that means for element of. So you're talking about some x interval, some x value inside that open interval. So take a look at what the second fundamental theorem states. It states that if you take the derivative of an integral, and it's a definite integral because there are limits of integration, and notice that your limits of integration go from a, so that's a number, and the upper limit is x. And notice what it tells us is that that derivative of that particular integral is simply going to be f of x. So to put that in normal English, basically all it's saying is that you take an integral of derivative of an integral, they undo each other, you end up with the integrand, remember that's your integrand, evaluated at this upper limit of integration. All right, notice how that's now in there. Now we're going to do a little mini proof of this to show you that it does actually work out, that when you have an integral derivative combo thing like this, that it actually does work out. All right, and we're going to work through a little example proof of that for you. This often shows up on the multiple choice on the AP exam. It's one of those I could bet you my next paycheck you will see one of them at least. And I think you need to be able to spot them, because if you identify them when you see them, they are like the easiest and fastest questions to answer. Unfortunately, a lot of people don't recognize it for what it is and end up doing it the long way, like we're going to do it in a second with this example proof we're going to work out. All right, so the one I thought we could work out is if we were to do the derivative of the integral from -1 to x of t squared plus 5 dt. And we're just going to take it in bits and pieces, so let's maybe do the integral part first. All right, that's like what we learned yesterday, so I'm just going to keep the derivative notation out in the very front. And I'm going to go ahead and evaluate this integral. So that's basically applying the first fundamental theorem of calculus. Antiderivative of t squared, of course, is going to be 1/3 t cubed. Antiderivative of 5 is going to be 5t, and we're going to evaluate that from -1 to x. So again, remember what the first fundamental theorem of calculus told us yesterday. We're going to substitute in the x first, the upper limit of integration. All right, so I'll write all that out for us. So that's 1/3 x cubed plus 5x. All right, then remember it's always minus. Now we're going to substitute in the -1. So I'm going to go ahead and do all that number crunching. So that turns into a -1/3 minus 5. All right, and maybe I'll simplify a little bit inside those square brackets. And let's see, this becomes plus 16/3 when you combine your fractions. All right, so now we want to do the derivative of that. All right, so derivative of 1/3 x cubed, of course, is going to be x squared. Derivative of 5x is going to be 5. Derivative of the 16/5, of course, is just 0. So we end up with x squared plus 5, which, geez, is same as our integrand with that x in there. Quod erat demonstratum. It has been demonstrated. You'll see math professors using that in college. It goes at the end of a mathematical proof. QED. Quod erat demonstratum. It's Latin for it has been demonstrated. So it's kind of neat how it actually works out. So this is what I was saying. If you can actually spot these when you come across them on the AP exam, I mean, you just literally go from here right to the answer, down there, can't draw my arrows. You don't have to do any of this work, but that's the problem. A lot of people don't see it for what it is and ends up going through all this, and then they get to the end and it's like, oh, that's what it was. So definitely kind of train your brain to look for these second fundamental theorem of calculus problems. All right, so let's try a couple. So the first one, we want the derivative of the integral from 0 to x of the square root of t squared plus 1 dt. So applying what we now know from the second fundamental theorem, that's simply going to be square root x squared plus 1, and yes, you're done. It never ever matters what the lower limit of integration is. As long as it's a number, doesn't matter. It can be absolutely anything. The reason it doesn't matter is because what you saw happen up here. Remember when you substituted in the 1 as the lower limit of integration, you got this stuff here, and when you took the derivative of it, it became 0. Right? That's why that lower limit of integration really never matters. All right, well, let's try the next one. All right, now the next one, I've tried to throw in some different ones that you're going to come across. We're doing the derivative of the integral from x to 3 of square root of 1 plus t to the 4th dt. Now, remember, according to the theorem, the lower limit of integration has to be a numerical value. All right, so the first thing we have to do is use one of our properties that we learned in a previous lesson, and we're going to negate this whole thing and thereby flip around the limits of integration. Now you can go ahead and apply the second fundamental theorem, because now you have everything in the order you need it. Just don't forget this negative that you had out in the front. So now your answer is going to be that negative square root 1 plus x to the 4th, and that's it. Pretty simple. All right, so this one. So now we want the derivative of the integral from pi over 2 to x cubed of cosine t dt. Now if you take a look at all the previous problems, notice how that other limit of integration was always plain x. Even back here on the example, like little proof we did, and even back at the fundamental theorem itself, this was always plain x. When it's not plain x, there's a little trick you got to do, but of course I shall tell you what it is. All right, so you're just going to go ahead and apply the theorem as you typically have. So we know that we want to put in this upper limit of integration in for t. So our answer is going to be cosine of x cubed. But then we have to multiply this whole thing by the derivative of that upper limit of integration. And the reason is because you're doing the derivative of an integral. All right, that's really kind of a good way to think of it. So you just have to multiply it by 3x squared, and that's your answer. You can just leave it like that. 3x squared cosine of x cubed. All right, so anytime the upper limit of integration is not just plain x squared or plain x, notice the derivative of x is 1, so technically you're multiplying by 1, which doesn't do anything. So if it's anything but plain x, you need to multiply by the derivative of that upper limit of integration. And the neat thing is it always works. All right, so how about the next one? Same kind of scenario. We're good on the lower limit being 0, so that's okay. Everything's in the right order we need it. So we're just going to go ahead and substitute this x squared in place of our t. Now you have to remember this was t squared, so we're going to end up with x squared and then squared again. Okay, so we'd have 1 over square root, and I'll write it all out for you. So it's the x squared that you're putting in place of t, but then you need to square that. And now you have to multiply by the derivative of that upper limit of integration. All right, so in the end, our answer, we can write it as 2x over. Of course, we can eliminate the parentheses, make this x to the 4th, plus 1. Yes, it's that easy. Don't knock it. Take it for what it is. Now, the last one that I want us to take a look at, it's in your textbook, so if you could go ahead and grab that. It's on page 407, number 43. This is just a really good application type of problem. We're going to be seeing some more as we wrap up the unit. I have a whole packet of like AP-like type of problems related to all of this. But this was one in your book that I thought we could do together and walk through. If you take a look at it, notice how you're given, you're defined this capital F function to be the integral from 0 to x of f of t dt. And you're given the graph. The graph you're looking at there is that of f of t. All right, so some little hints for working through this and how to think through it. All right, notice what you're doing is that you're defining this capital F function as the integral of this other graph you're given. So if you think of what the easiest way to think of this, think of the f of t graph as like the first derivative of the function. And that makes capital F the original. Because one reason you easily can do that with this, really because of how they're defining this capital F function. And we know that if we do an integral of something that's a derivative, we get back to the original. We know that to be true. So if you can think of this graph that you're looking at as that of like the first derivative, and this capital F function we're talking about as the original, then it's really just like those problems we did back in what Unit 3, was it? I guess. Remember when you're given the graph of the derivative and you're asked information about the graph of the original? That's really all this is. They're just presenting it in a very, very different way. All right, so we're going to go through, and I think as we answer some of these questions, you're going to see how much like it is what we did before. All right, so letter A. So where do the relative minima of capital F occur? All right, so you have to think where that would happen. So relative, let's see, we're talking minimum? Okay, relative min. All right, so think of how we answered that question before. All right, remember we would be looking at the graph of the first derivative, and we'd want to know where the relative minimum of the original were. All right, so think about what we would look for on that derivative graph. And didn't we always look to see where that derivative changes from negative to positive? All right, so look at this graph. Because remember, that would mean the original goes decreasing to increasing. All right, so take a look at the graph. Where does that happen at t equals what? I think there's only one place it goes negative to positive, and that's going to be at 3. All right, so the way in which we're answering these are really just like how we thought through them before. All right, now the next one asks us about the relative maxima. All right, so think about what we did before when we were given the graph of the derivative, how we knew where the relative maximum were. What were we looking for? All right, weren't we looking to see where that derivative goes from positive to negative? Because remember, that means then the original is going from increasing to decreasing, therefore creating that maximum you want. All right, so take a look at the graph and see where that happens. Any place where it is the graph that you're looking at here changes from positive to negative. And that's going to be in 2 places at 1 and 5. All right, now the next 2 questions ask about the absolute extrema then. All right, now remember where we always said this is going back to, lesson 3.1 maybe it was? Maybe, I think. Absolute extrema, remember, can occur at your critical numbers where the derivative equals 0, but also at the endpoints. All right, so you've pretty much defined the critical numbers here because remember, they're the ones that are going to become our max min points. But we do have to take into consideration the endpoint that looks on this one maybe to be at like 5.5 where that graph stops. So that's something we'll have to keep in mind. Now, another thing to think about when we've been talking about relative minimum and maximum. All right, we pretty much answered these in light of how we did it before, which is entirely correct to do that. But think of another interpretation of this. All right, if we're just looking at this graph and figuring, okay, this is a graph of f of t, and I'm defining this capital F function to be the integral from 0 to x. Well, remember we talked about another interpretation of an integral as being area under a curve. So really what you're defining is, you have this graph, and you're going to start at 0, and you're going to start finding the area under the curve as you move along the positive x-axis. All right, and depending upon where you stop, you would calculate the area to that point, and that's what you call f of x, capital F of x. All right, so like in letter A, where we said a relative minimum is going to occur at t equals 3, and take a look at the graph. All right, if I asked you to find the area under the curve going from 0 to 3, doesn't it look like it would have a lot more negative area because of that part underneath the x-axis? So we know that area would be negative. All right, hence it's a minimum. It's probably going to be, since it's a negative, it's probably going to be a minimum. All right, if you take a look at just 1, that'll be an easy one to do. All right, we said a relative maximum occurred at 1. Well, if I asked you to calculate the area from 0 to 1, it almost looks like a semicircle kind of. But we know it's going to be positive and maybe a teeny tiny area. Okay, but it is a relative max. It's higher than any area that would be if we were to keep going a little past 1. It is going to be higher than that because anything past 1, then you start taking area away because now you're underneath the x-axis. If you go all the way out to 5, all right, and think of these areas above and below the x-axis and how they balance out. Up to 1, you have a little bitty positive area, okay? Then by the time you get to 3, remember we talked about you have more negative area. All right, up to a 3, you definitely have negative area because that area is bigger underneath the curve from 1 to 3 than it is from 0 to 1. All right, now you go 3 to 5 though, and that's like a big positive area, which is probably going to offset that negative area that you had up to when t equaled 3. All right, and that's why there ends up being a relative max then of 5. All right, because all the way up to 5, you're definitely going to have a positive area. All right, so that's something we're going to think about as we go ahead and answer C and D. All right, so letter C asks us to find the absolute maximum. So remember where your absolute max could occur. It's you. It could be where our relative minimum were at our critical numbers. So let's see, where was the relative minimum? T equals 3. All right, we know they were maxes at 1 and 5, so I'm not going to include those here. We are doing, this is minimum, I'm sorry. C is a minimum. I wrote it wrong. No, C is a maximum. Darn it. I can't read. Why do they go minimum and maximum in A and B, and then they mix it around and go the other way? That's really annoying. All right, so this is going to be 1 or 5. All right, because that's where we knew we had relative max. Or, remember, they could be at the endpoints. So maybe the best way to answer this is to sort of think of that area analogy, okay? Well, take a look at your picture again. All right, we talked about up to 1. That's going to be like a little itty-bitty area, all right? Going all the way out to 5, that's definitely going to be more positive area than 1 was. All right, so 1's out. That can't be an absolute max, because remember, absolute max means it's going to be the absolutely biggest area up to that point. All right, so up to 5, we know we have a positive area, okay? So it could be 5, could be. All right, but remember, we need to consider the endpoints. Well, if we started at 0 and didn't go anywhere, we don't have any area, so it can't be 0. The endpoint, if you take a look at where this graph ends, look how it ends a little, maybe like 5.5. But what's going to happen to your area as you start moving to the right of t equals 5? Because we set up to t equals 5, there's definitely going to be positive area. But as you move past 5 to like maybe 5.1, 5.2, now it dips below the x-axis. So now you're taking area away. And that's going to make that area at those points less than the area you had at t equals 5. So the absolute maximum has to be at t equals 5. If you need to hear that again, you can go replay it. All right, now we're going to do absolute minimum. All right, so let's talk about where absolute minimum could occur. And we only had one relative minimum, so that was at t equals 3. And we know the other x-intercepts produced maximum, so it can't be that. But remember, it could also be the endpoints. All right, so let's kind of go through the same thinking. So up to 3, we definitely know we have negative area. Okay, so that's some kind of negative something. All right, so it takes care of t equals 3. That could be it. If we consider the endpoints, well, if we did 0 to 0, we don't have any area. But something negative is going to be less than 0. So can't be the endpoint at 0. If you go over to the endpoint at past like the other end at 5.5 or so, well, we talked about how up to 5 you're definitely going to have positive area, and then you just gradually start taking away from it. If you were to stop at a t-value of 5.5, where it looks like this ends, you're not going to be taking enough away to get as negative as you were at t equals 3. So it's going to have to be at t equals 3 that the absolute minimum occurs. All right, so as I said, hopefully that makes sense. If you need to hear it again, I would stop this and maybe replay it. All right, let's try E. All right, now we're talking concavity. All right, so maybe let's do concave up first. So as we did before, we can talk about how we know where that's going to be. All right, so remember back to the other problems where we were given the graph of the derivative. If we wanted to know where the original graph would be concave up, remember that was always where the derivative was increasing. So in this case, the derivative is little f. So the big F function is going to be concave up wherever the graph of little f is increasing. All right, and think about it relating to how we did it before. If we were given the graph of the derivative and we wanted to answer the question where the original was concave up, we always talked about that's where the derivative graph was increasing. Well, in this case, the derivative graph is the little f function. All right, so if you take a look at your graph, we want to figure out where that's increasing. And I think there's two different intervals. And remember, concavity is always open intervals, don't forget. So this one looks like it's about maybe 0 to 1/2 for the first one. And then the other interval 2 to 4. All right, so now we want to answer the question about where big F is concave down. So that's where little f is going to be decreasing. Again, drawing that parallel to what we did before. If we were given the graph of the derivative and we wanted to know where the original was increasing, or concave down rather, we wanted to figure out where that derivative graph was decreasing. Now in this case, the derivative graph is really the little f function that you're looking at. All right, so there should be two places for that, and it should be from 1/2 to about 2. And then the other one goes from 4 to about 5.5 maybe, if we assume that's where the graph stops. And just remember they're always open intervals. So this was a really interesting problem because it kind of had us flip-flopping between different interpretations of an integral, of a graph. If you think about this last one we did, this is a lot like what we did back in Unit 3. Given the graph of a derivative, figure out where the original is concave up or down. All right, very, very similar. But when we're talking, especially I think anyway, the absolute max and the absolute min, at those times it's almost easier to think in terms of the area under the curve and that type of interpretation. So that's why I thought this was an interesting problem, because it really had us thinking on two different levels within one problem. On one hand, and in some parts like C and D, we were talking and thinking about this as the interpretation of area under a curve. But when it came to like part E with the concavity and parts A and B, it was almost easier to think of it like the old problem we used to do, where we're given the graph of the derivative and we're trying to find out information about the graph of the original. And that brings us to part F, of course, sketch the function of capital F. All right, so let's set up some axes for us. And we know our x values, 2, 3, 4, 5. You don't have to worry about y values, that's okay. Doesn't have to be perfect. And we're really just going to do this like we did it before. All right, remember we figured out before there was a relative maximum at 1. There was another relative maximum at 5, but remember that ended up being the absolute maximum. So I'm going to put that like up really high, like all the way up there. All right, so here's 5. All right, our minimum, we only had 1, and it ended up being an absolute minimum at 3. So I'm going to put that like down really low, because it's got to be the lowest point on the graph. These points in place, we want to keep in mind the concavity. All right, so the first concavity we had, starting at 0, remember it was concave up from 0 to a half, but then it changed to concave down. All right, so let's see. So starting here has to be concave up till we reach, there's about a half, and then it changes to concave down. So this is like our inflection point right there. And then starting at 1, remember from 1 half, from a half to 2, it's going to be concave down, then it changes to concave up again. So remember, we're going to have another inflection point here at 2. So remember how we talked about placing the inflection points? Like we should be able to place it like halfway between this point at t equals 1 and this one all the way down here. So maybe around there should we target. All right, so here's our concave down, and then it switches to concave up. And let's see, then it's going to be concave up till 4. Here's 4, so like halfway between this really low point and this really high point. Maybe we can just have it crossing like right near the x-axis. So concave up, now it switches to concave down. And there's about 5.5 maybe. Maybe I kind of overshot that a little bit. So that's what the original function f would look like. So tonight for homework, if you please, it's on 2 different pages. There's a couple pages from last night's homework. There's one problem similar to this number 43. It's this one, number 31. So that's another reason I wanted to do one similar to it. So if you could work on these tonight for homework, I'll be having you check them tomorrow in class on your own. And thanks for watching. Please feel free to go back and listen to selected parts if you need to. Otherwise, I'll see you soon.